The phenomenon that won the Nobel Prize in Physics this year, entanglement, is certainly obscure and mysterious to most people. But it is also at the heart of the branch of physics known as quantum mechanics, which describes the microscopic world and is of great interest for applications starting from cryptography and quantum computers. First of all, it must be said that defining entanglement without the language of mathematics is difficult. This is the beauty of mathematics. Sometimes with just a few lines, it is possible to explain complex concepts that spoken language struggles to describe. Entanglement must now be interpreted as a physical quantity, such as time or energy. It must be interpreted as a resource that can be useful in practical applications. When we talk about quantum entanglement, I like to use the synonym quantum correlation. Entanglement is in fact a stronger correlation than any classical correlation that is described by classical physics. Quantum physics allow for the existence of strongly correlated objects. For example, let's imagine two friends, Alice and Bob, each of whom has a coin. When Alice tosses her coin, she has a 50% chance of getting heads and a 50% chance of getting tails. The same thing happens to Bob. When both Alice and Bob toss their coins, we have 4 possible configurations, each with a 25% chance. Heads and heads, heads and tails, tails and heads, tails and tails. It is important to note that Bob's result does not depend on Alice's and vice versa. So far, everything is obvious. Now let's imagine 2 special coins. Coins that exist only in the world of quantum physics. Let's call them quantum coins. These quantum coins have a property that is difficult to understand. Let's say Alice tosses her coin and gets heads with a 50% chance. The 2 quantum coins are special because in this case, Bob would also get heads when he tosses his coin, guaranteed with a 100% chance. The same thing happens if Alice gets tails. So, for Alice and Bob's quantum coins, there can only be 2 configurations, heads and heads or tails and tails. The 2 remaining configurations, heads and tails and heads, are excluded. The quantum coins just described are not a product of our imagination, but they can be constructed in the physical world. For example, through 2 photons, the fundamental components of light, or through atoms, the fundamental components of matter. Heads and tails can be encoded in the properties of a photon or an atom. Astounding.